Okay, I thought I would show you. We talked about this last time. This little rule with shear walls, that there always has to be a minimum of 2 points of intersection for them to be stable. So this just demonstrates it. So this would be the second one, no points of intersection. I mean, even if you had 3 of them, right? Obviously, that just collapses. That's not going to work. If you had an arrangement like this, I guess this is the first one there, it does have 2 points of intersection, right? And that makes a huge difference. That then is suddenly stable. Well, let's you do that. Let's see. If we had 4 of them in a box, of course, that would be stable. This is the one that's kind of questionable, that you'd almost think would be stable. If I can make it stand up here. My box is a little uneven. Okay, so this would be, if I can get it in the right direction, they should all be intersecting right there. And this one doesn't. If you have a force that rotates around that point, then that's not going to do it. And of course, the one, even with 4 walls, if they're coming together at that point, that's going to do the same thing. They'll collapse like that. So that just kind of demonstrates that. Okay, which is kind of interesting that it really is. I mean, like you can recognize a pattern immediately. When you start out, make sure you've got at least 2 points. You can have 4 points or 5 points or anything more, but at least 2, or else it's not going to be able to be stable. Okay, we talked about this a little bit too, just the definitions. The diaphragm, of course, is this part here. It can also be, it doesn't have to be flat. Like most residential roofs are sloped, right? And that can also act as a diaphragm. It's just out of plane. So whether it's like that or like that, it'll still act as a diaphragm. In fact, by the calculations, as far as the moment calculations, you can look at it in the projected area, the same as we do the projected rafter design. It makes the calculations a little easier. Right, so that's the diaphragm. The shear walls are what attached to it, right? They're over here. Oops, I guess we need a couple more, and this is then the collector strut. This would be at the top of the shear wall, the collector strut. The shear walls in shear, you can see one side's going to be in tension. It's got to be held down, and the other side is, as it gets that shear applied, there's a moment, right, that's twisting it, that would push it up. Let me just do this on the diagrams. So this is, and the wind can come from either direction, right? So if I've got the wind blowing in this direction, then this is my cord. Those are my cords, the same as the nomenclature in a truss. This then becomes the collector on the side. It's collecting this shear force, right? That's what it's collecting, and it's transferring it from the diaphragm onto the shear wall. So it collects the force out of the diaphragm and places it on the shear wall below, down here. See? So the force is going from up here, to being resisted down here by the shear wall. And of course, if you rotate it, everything just follows the load. So now the collector struts are on the side. The shear is over here on this edge, on the long edge, and resisted by. So you've got to have that shear resistance, obviously, in both directions. You never know which way the wind's going to blow, so you've got to have it designed for the worst case in all 4 directions. The other thing that affects the strength is called blocking. This is just how it's fastened down. So the edges are always on a member, right? On a joist or on the edge. So the edges always get nailed down. In this case, there is blocking. This is the blocked case. So all of these edges are nailed down, not just the perimeter edges, but the edges of the panels here. But here, look at this. The joists are going like this, so there's no way you can nail this, right? There's nothing there. So this edge of the panel would not be nailed. The edges here would be, if the perimeter still is, but here, look at this middle panel. None of the long edges are being nailed. There's nothing under them. So of course that's a little bit weaker. It would be stronger to put the blocking in there, and these are separate. You know, you've got the joists running, right? The blocking is just pieces that get nailed in there, but they're separate little pieces that you've got to nail each one in all the way down the line. So that's a lot of work to do that. So it ends up being much. Well, I don't know how much more expensive, but more expensive. It's definitely more expensive to do that option. So if you can get away with it, if it's strong enough, it's generally unblocked. And from what I've observed, I mean, if you kind of look at construction going around, it's usually unblocked. Seems like it's what I see done. You don't see that blocking, like when they lay the trusses, and you'll see them put the trusses down, then right on top of it the sheathing. They don't come in and put a lot of blocking in there. That's just not usually done. So usually the cases seem to be unblocked. But if you need the strength, then the blocking would give it to you. This is just, illustration out of the X305. Oh yeah, these are the two. I don't know if I mentioned that at the beginning. These are both posted, but the X30, this one, has the most information. It's specifically an APA doc on lateral design, right? So the diaphragms and shear walls, it covers those two. And it's mainly got a couple of tables in it that we'll use in a little bit to do that. This one also, diaphragms and shear walls. I think it has those tables, so it has much more explanations. It's got some of the equations. Yeah, a little bit more about the nailings and that kind of thing. But that one also has design tables in it. Okay, so let's see. Yeah, like this one. This design table right here comes out of the 305. And this is to find the shear in PLF that the panel can withstand. And this is for diaphragms. So there's a table, apparently table 1 is for diaphragms. I think there's a second table 2 for shear panels. So for the diaphragm forces, if we just take an example, okay, say we have a wind load that's applied at the top edge, right? It's this would act as a deep beam. Okay, this would be the shear force then, 120 times 60 divided by 2. This right here is what's coming out to 36,000, I hope, pounds. So that's that reaction force, so to speak. You divide that by 20, and you get what the shear force distributed across the length of the diaphragm would be, right? The total is 3,600, but divided by 20, I guess, is 180 PLF. So that's where that's coming from, that 180 PLF. So what you want to do then, what this table does for you is sizes a panel, gives you what panel and what nailing spacing is able to resist or provide that strength, that 180 PLF. All right, so assuming that's what we're after is 180 PLF, then you've got several choices here. First, you've got the blocked or the unblocked, right? That divides it right down like that. Okay, so the one side's blocked, the other side's unblocked. Then you've got a structural grade plywood, or you've got the APA rated sheathing. This would be the one, we looked at those stamps like the 2040 or the 2060 or whatever, however it's rated. No, I'm sorry. What am I thinking? They're rated by this band. 1620 or 1624 would be one. The spacing of the joists. Anyway, that rating, that's the normal type that's used. This would be more expensive, right? To have it a structural grade. This is probably the one that's much more common. Okay, then you've also got these cases down here, right? This is how it's attached to the framing, to the joist, whether blocking is, if it's used, and all these different. So you've got four. You have to look at them kind of closely to see which matches your situation. So in this case, I'm just going to assume it could be any case, but normally you'd look and you'd be designing it for a specific case probably. Okay, or it may be that it has to be two cases. If it takes the wind from one direction, it also has to be from the other direction. So it may be two different cases. Okay, so you're making all these decisions. We'll go, let's say we'll take it as this, right? We'll be in there, and let's try it first as unblocked. So if we got 180, and then the other thing you've got to look at is this. This is the width of the framing member, right? So either 2-inch or 3-inch. Well, in this example, I'd say 2-inch. In most cases, it's 2-inch. So I'm going to leave these 3 inches out. I'm not going to look at 3-inch. So I'd go, I need 180. I'd start at the narrowest. These are from the thinnest to the thickest. So I'd go, oops, I'm sorry, this was the thickness. 170, no. 185, yeah. Okay, so this is blocked. I could use a 3/8 panel with 6-penny nails at, that penetration. Okay, so 6-penny nail, and they'd have to have this nail spacing. So they'd have to be 6 and 6. So that's actually the widest nail spacing for the block case. Okay, and if I did it unblocked, that's what I was going to do originally. Okay, this fails, this one would pass. So you can see the unblock. It's actually also 3/8, but I have to use a bigger penny nail, heavier nail, and this is case 1. Okay, so for case, come on. Shoot, what the heck? All right. So this would be case 1. I'd be able to do it with this panel. If I didn't want to follow case 1, which you see has a lot, it looks like the more, it's supported in the strong direction, or it's acting in the strong direction. If it maybe was one of these other cases, then I'd have to go a little bit further. That one would fail. That would fail. I'd have to come down here. So that would be that one. So depending on, you can see you've got your choices then. What case it is, and whether it's blocked or unblocked. There is that online problem that we're doing this week. Includes this, but I think it doesn't leave so many options open. It tells you whether it's blocked or unblocked. It tells you which case and everything, I believe. Okay, so here's another one. Let's see, what's this one? This one's blocked. Maybe the other was supposed to be unblocked. This one would be blocked. It's got a little heavier load, 200. A little bit longer span, comes out to 7,000 at the reaction. So this is 350 then, right? Oh, I'm sorry. That's the 7,000. WL over 2 is that reaction. That's the 7,000. I divide the 7,000 by 20 feet, and that's where I get the 350, right? PLF. And that's the number that then I have to read out of this chart. And if I'm doing it for blocked, okay, so first we get rid of all the, get rid of those. I'm going to use APA rated, I think. So I'll say we're not using that. So if I'm in this category here, using 2-inch members, and I gotta get 350, that would fail, 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 fail. Whoa, all those fail. So then I come to the next set, fail, 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 fail. Woo, finally. That one would pass. So that would be 15-30 seconds at 8 penny nails. And that should be the lightest one. I mean, you start, and this would mean the nail spacing 6-inch and 4-inch at the whatever the other boundaries here. You have to read all that, but those are the nail spacings. 6 inches at the edges, and no, at other panel edges. 6 inches at the boundaries, 4 inches at the boundaries, and 6 inches at the other edges. Okay, so that would give us a panel. You can see there'd be other options. Maybe you could go with this was 15-30 seconds. We could put more nailing on it and get away with this guy up here, right? That one. So I could drop it down to 3/8. Actually a smaller nail, but it would require closer nail spacing. Now I've got to have 2.5, and I've also got to pay attention to that footnote C, whatever that is. This down here. So normally you take the first one you come to. Certainly in that online homework problem, take the first one you come to. Okay, so those are diaphragms. Those are all the roof part, right? Now we'll talk a little bit about the shear walls on the sides. There are generally 3 types. This is probably the most common. This is rather expensive, and this is kind of weak. So this would be your first choice, I guess. If you really needed the strength and you had large openings, this one would be possible, but it includes these steel straps that these guys that have to be placed on the wall, and which is kind of an expensive procedure to do that. So that is probably less common. The problem with this one is that this edge is not braced. Here it is. These act independently. You've got a shear panel here. That's why it's called segmented. It's got 2 segments, or however many segments are divided by windows, right? If you didn't have any windows, there'd be no problem. You'd just have one big shear wall, and that would be simple. That would be, you'd use the case of the first one, but there would be no window. It would just be one big piece. You'd have supports at each end. Or it would be like this bottom one, if you didn't have the window, would be completely strong. But here, on the bottom one, if I've got a force, like say the force is going this way, then this is going to go into compression. Whoops, I'm sorry, maybe I should make it the other way. Sorry, let me do it this way. If the force is going that way, then this is in tension, right? Which is where the hold down is. This is in compression, which would be okay. It would be able to withstand the and compress down. That's not a problem. This would be in tension, and that would be the problem. There'd be no hold down for that one. So that's the problem with that. Okay, again, the nomenclature, collector strut goes at the top. In this case, we're calling the chords the sides. All right, and there are proportions to these, a limited width to height ratio, and that is in the what they call spidwiz. Is what it's called. This is, and I don't know if I posted this or I think I may have posted it. I have to go back and look. Maybe I didn't. I posted the tables out of this. There's only really one table that you need. But this is the special design provisions for wind and seismic from the American Wood Council. So that's part of the NDS set. This one, spidwiz. Okay. So, in fact, this is the table that I was just referring to out of the spidwiz, and it gives this wall aspect ratios. So for unblocked, you've got to have 2 to 1. For blocked, it can be a little bit wider. You can have 3.5 to 1. Right? That's the minimum, or excuse me, the maximum width that's allowed. So if you go beyond that, it's maximum. I'm sorry, it's the maximum aspect ratio, but it then translates into the minimum width, is what it actually finds. Okay, so for this is the type 1 segmented. You are still allowed to do this. This is the older method. You know, if you look at the old balloon framing, it was before plywood really came into general use. They would brace them with these diagonals at the corners, and yeah, it's a much more expensive and not really as effective method. So it's almost never used now. In fact, they kind of drew it wrong here. It would be, the way that works is you've got the verticals like this, and then you've got to actually cut this in, right? It's got to be inset. It can't sit on the outside of the wall, or you can't put the sheathing on it. So it's you've got to cut these in so it sits in here. And it goes like this then. If it went like that, you'd be chopping the member entirely in half, but it doesn't. It goes like that. So it's a lot of labor to do it, and it's not as strong. So that's probably not a very good option. The wallboard, this is if I need to get a sample of wallboard, and I saw there's a project going on right now on Depot Street. If you ever drive down Depot Street, you know, across from the train station, up on the hill, there's a big, they're building another apartment building, and it must be 3 or 4 stories high. It's all framed, light framing, and right now they're putting on wallboard on it, that green board. That, you know, that guy that we saw that video comparing the OSB to the plywood, and he talked about, you know, you can put the plywood at the bottom and OSB. And his comment at the beginning was wallboard, yeah, that's allowed, but it's like better high-grade cardboard or something, I think is what he said. He didn't think too much of it. But it does get used. It's like three times weaker than, or the, regular wood panels. OSB is 3 times stronger than the wallboard, so it's not terribly strong. But if you're going to cover a whole, that one they're doing now has very small windows, and they're covering the whole facade with it. So, okay, I guess they've got enough surface that they get their shear resistance. They're doing it with the wallboard. Anyway, and then these are the structural wood panels. Okay. Yeah, this requires an 8-foot length. Huh. Okay, so how you get... Yeah, I'm not sure, because that doesn't look like... I would have thought... Oh, maybe they mean vertically, length vertically? Oh, yeah. Oh, of course. Yeah, now I remember. Yeah, these, although they're shown in 8-foot height, you can turn the plywood panels on their side, right? And if you had a 12-foot height, that would be a multiple. Or if anything, even if you had a 10-foot height, you'd fit 2 in and then a strip of 1 or something like that. A 2-foot strip. So you're allowed to do that with the plywood, but you can't really get away with that with the wallboard. Okay, so here's type 2, right? This is that one with the collector struts, and the a little bit more trouble to calculate too. You have to first design these steel straps, or at least pick them out of a table. They get inset and nailed onto the framing, and then essentially you've got each one of these little segments as a separate shear wall, and you calculate the strength of each of these and add it all together. So that's, in terms of calculation, a lot more trouble. It ends up being a little bit stronger than the segmented, because you're picking up some additional strength from that middle part, but unless you really needed that strength, that probably would not be the best option. Okay, and this is the type 3, the one that, the perforated one. This is the one, yeah, here I drew it this way. So if the force is going this way, this would be tension, and it would have the hold down here. Okay, so that would be correct. This would be compression, and it's just pushing on it. This is the one you're missing. It should be another tensile force, right? But there's no hold down. So you lose that. It has a little bit of strength, obviously, because the sheathing's holding it, but they say it only has about 25% of the total. So this would be approximately 25%, and this would be carrying 75%. So this would be much stronger. There is, in calculating that, there actually is a factor, and you have to go to the IBC. I don't think it's in the SPIDWIZ. I'll have to look, maybe it is, but in the IBC they give this factor that lets you proportion the load between those two, and it depends on the width and something. Anyway, but that, of course, would also not be, I mean, for the price of this isn't that expensive, my heavens, that you can't put that piece in. Well, you have to put them in both places, because, of course, the wind could be from either direction. But still, it seems like you'd go with the segmented there. But maybe if it didn't require the strength again, okay, I guess that's certainly an option. Okay, now looking a little bit more at connections. Right. These, yeah, this is a no-no. You shouldn't rely on just toe nailing to hold that end strut down. You know, these you do toenail. Oops. Right? Those you can toenail. But the ones that are really trying to hold the tensile force down, you need a bracket. And the reason is, you've got to put that nail in some direction. It's only going, you can see if the force comes from this direction, or if it's an uplift force, which is very likely, that is the force that you're resisting primarily, because if it's a downward force, it's just pushing on it, then that's not a problem. But it's the uplift force that you really got to worry about. So that would be a problem. The toenail wouldn't hold that. So that's why you've got to have these special brackets. They show them as little angles, but usually they go quite a bit higher than that because they've got to develop the strength in the connection, which usually takes a lot of screws or nails going up to get that strength. Then they get, these anchors are probably cast into a slab, right? I guess you can, they have a pull-out strength, and however you do them, if you cast them in, I guess you can develop the strength of the bolt, which would be ideal. If you just drill them, I don't know, you have to look up what the strength is, but they have a pull-out strength. Although that's critical for this one, that pull-out strength. These take primarily a shear force on them, so that's not quite so critical. I guess maybe you could get away with drilling those, but very often they're cast. They're cast into a slab. Okay, and here, yeah, nailing specifications. Okay, that's a few more diagrams explaining out of the 305. This looks at the segmented type, right? And here's this height to width ratio I was talking about. This is actually for blocked. I think for unblocked, if I remember right, it's h/2 for unblocked. So you've got a choice of those two ratios. And let's see, the things that you would design, the panel thickness is primarily going to come out of a table, and the grade and the nail spacing, all that comes out of the table. These base anchors, so this would be out of the APA table. Oops. Is where you get that. These base anchors, the manufacturer will give you the specification of the anchors. So this would probably be Simpson or somebody like that that manufactures the anchors. They'll give you the strength, but then you just have to follow that, their guidelines, and you have to calculate the force that's going to be on them, obviously, to find which ones you need. Right, that goes also, that's both for the base shear and the hold downs. And their placement, okay, and the fastening at the edges, that's the cords. Oh, yeah, the attachment, the nailing spacing on the cords, and you also ultimately have to design the strength of the cords, the strength of in the diaphragm at the top. Those collector struts have to be designed, and in a shear wall, I guess what we're talking about now, the shear wall, you have to design the strength. But usually, they're not that high if you have the full area in tension. That gives you, and maybe they're doubled. It's a matter of whether it's a single or a double, but they're almost always doubled at the corners anyway. So if you've got them doubled, they're probably going to be strong enough. Oh, yeah, when you double them, you have to go through that nailing business. Remember we talked about that with those wasn't it the columns where you've got to nail in a pattern alternately? So there's a lot of nails that get put in them. Okay. Top plate. All right, this is the drag strut. This is called sometimes it's called a drag strut, sometimes it's called a collector. I can't write very well. Man, this pen's getting worse, isn't it? Collector struts. It is the top plate, so it's a top plate which acts as a collector strut, which is called a drag strut. You know, it goes by any of those names. A double top plate, in fact. All right, this is why it has to be doubled. Well, part of why, we talked about this before too. If you've got, you know, if it's acting in tension and you've got them, they're only 8 feet long, they come together somewhere, they're not going to have a joint there. And I think you can get straps that would do that, but you end up making them doubled anyway for the flexural strength between the joists, as a rafter would connect them. So they end up being, you know, put on like that. You just have to make sure you don't put them, that somebody doesn't get the bright idea of lining them up. That would not be good. They've got to be staggered. That top plate has to be staggered so that they're able to transfer the force. So there is a force. This is the force coming from the diaphragm, right? The diaphragm there, and then this is back on the shear wall below. And it gets transferred from one to the other. If you've got a discontinuous wall like this, you've got the force is not going to make the corner there very well. You've got to pull that. If it really is, if this is really acting as a shear wall, you've got to pull that tensile force on across to the other side. So you usually have in the floor that continues. You'd probably have a wall there, presumably, or you have to design the floor plan so that works out maybe a little better. But those drag struts have to go all the way through. Okay, and a little bit of details on the tie downs. This is what they actually look like. This is probably from Simpson, I would bet. They make some, and they have a lot of attachment, not just a couple of bolts usually, but a whole series of screws that go up. The ones I've seen, maybe I got a picture of one later, they're usually segment, you know, like they've got 2 strips that come up and nails that go down in a staggered pattern, and then they get bolted down, and those are cast. Usually you can have those cast, but at any rate they have to develop, however you anchor them, it does have to develop the tensile strength that you're trying to get. Okay, down to the still plate. Yeah, you definitely just can't screw them onto the sill plate. They've got to go on down to the concrete because it's a little bit more force than that. Okay, so here is, I think the other table we looked at was diaphragms, was that right? Or okay, this is table 2 that's looking at the shear walls. Again, it's finding, it's finding PLF for you, or you, I guess, you give it PLF and then choose the panel size that is able to, panel size and nailing that's able to do that. This table includes a situation where it's applied over gypsum sheathing, and this would be, they might use gypsum in there as a fire break layer, you know, a fire proof layer. And if I understand this, I can't think that I've seen it very often. You'd put the gypsum down and then you'd put the plywood on top of it. This would, I assume, be on the exterior, because you wouldn't do the opposite. That would be a disaster, because the gypsum would melt right in the rain. So if you had the gypsum and then the plywood over it, then the nails have to go through the gypsum to hit the studs, and it makes it a little bit weaker. So this is, I presume, a little bit weaker, although the numbers don't seem to be that much weaker. Okay, so that's a distinction there. Then you've got, again, structural grade. You've got the APA rated grade, and this is simply siding. So, okay, if we were doing a commercial building, I guess here, shear wall with gypsum for a fire rating, and we're required to get 437 PLF. Okay, let's see if we can do it. That's going to be quite a bit. So starting at this end, no, 437, yeah, those all fail. Where'd it go? Oh my goodness. Okay. 437. Okay, this one passes. So that, I think this one almost passes, 430, but not quite. 300. Okay, so this one would make it. This would be nailing at 3 inches on center with 10 penny nails, and it would be a, no, that's the penetration, sorry. 7 16ths. Oh, that's a structural. Ooh, I didn't want to use the structural. Okay, but that would be with the structural. If I didn't want to use the structural, could I get away with that? 437, I'd have to come all the way down here. Okay, so if I wanted to do it with rated sheathing, well, actually, that's the same thickness. And it's also the same nails. Wow. Okay. It's a little, yeah, it's quite a bit weaker, but in my case, it would be strong enough. So that would definitely be probably the better choice. The rated sheathing would be less expensive than the structural. Okay, so you can see how you pick it out. You're normally just going down the list and pick it out of the table. Okay, and now, all right. This is why I've been kind of rushing because I want to get through this example. This is the example of the homework problem, the one that's online. And it is kind of a detailed problem. There are a lot of steps to it. And when I put that up there, where did I do that? Be sure to download this. This is, you know, at the before you go into the actual problem with all the questions, where it gives you all the scores and the numbers, the options, which case there's a little PDF file that you can download for the supposed to be instructions. Be sure to look at the instructions because it gives a very complete step-by-step, essentially this PowerPoint, but it marks which question applies. It makes it a little more clear where what the questions are asking. So make sure you got that, download that so you can, makes it a little bit easier to follow. Because these questions, when I put those questions up online, they can only be this long. I can't write a whole paragraph of what I'm asking there. Okay, anyway, here we go. This is what we got. We got a building, we got a wind load on it, we got a diaphragm up here, right? And we got some shear walls. Right, we've got these shear walls, and I'm basically going to design this middle one. I think I take that one. For some reason, I should have just made them all the same size. I don't know why I played around making them different sizes, but we're doing that one. So we're going to design the shear wall and design the diaphragm and check all the forces on the cords and everything. Okay, so. For a wind load, a 30 PSF, that's coming on in PSF. That means half of it's going to go down here and half of it comes up here. So I've got to have 8 feet, right, times 30 PSF, which will give me the load on this top edge up here, right? So this load on that edge is this load, that 240. So this is the 28-foot edge here and the 60-foot span there. And this is the way then it's acting as a beam. The diaphragm is acting as a beam, 28 feet deep, 60 feet wide. And I want to calculate, of course, the end reactions in the moment. So that's what this is. The end reactions are 7,200 pounds apparently. The moment comes out to be that in foot-pounds. If I distribute this force then across here, right, as a PLF type kind of shear force, right, that is where this comes from. So the total divided by the length is that shear force on the edge in PLF. Okay, so that's got that. That force, that shear force on the edge, is what I want to use to size that panel. So first I'm going to size the, this is for the diaphragm, right? I'm sizing the diaphragm panel. In my case, well, it says I used, oh, I did both, blocked and unblocked. On the problem online, it tells you whether you're, I mean, it doesn't give you this many options. It just says use either blocked, or it tells you what to use. Okay, so if I had a choice and I was using, I am using APA rated sheathing, and I think all the ones online do too, so I would get rid of these. I'm not going to use those, and that's leaves the rest of them here. I'm also not using the 3-inch, right? This is going to be 2-inch rafters, so don't worry about the 3-inch. And we've got to find 257. So if I'm considering it blocked, 257, that would be almost that one. So there's my 15/32 8-penny nails. So that should be this one, 15/32 8-penny nails. Okay, if I did it as unblocked over here, oh, I got 257. Okay, no, almost that one. That would be that one for case 1. Oh, did it say what case? Yeah, case 1. Oh, good. On yours online, I think I tell you what case. I think it actually specifies a case, so you don't have, I mean, you'd know exactly what column you're supposed to go down. You have to pay attention to that. But in this case, if I was using case 1, that would be the 19/32. That's that one with 10-penny nails, right? 10-penny nails. Okay, so that chooses the panel, right? Now we've got to think about the chord force. We've got to get the we'd have to design those top and bottom chords, or at least check that they are sufficiently strong enough, and this would almost certainly be in tension. First, they're weaker in tension, right? If you look at the NDS specs, the allowable tensile stress is always the lower of compared to compression. Compression is going to be stronger. So, and on top of that, I don't see how it could fail in compression. Compression, if you got the double top member, really both of them would end up acting, right? Because even if it is butted together, they'll butt together then, and in compression it should work. But on the tensile side, that's not true. So even though you have a double top plate, the area is only 1 2x4, not 2. So okay, so we've got to get this force. We got to get that tensile force. We calculated the moment, right? The moment is we calculated from WL squared over 8, right? That's how we got it. But it's also equal to the couple here, so it would also be equal to T times the width, right? Times, in this case, 28 feet. Wow, man, this thing's driving me crazy. So jittery. Okay, so to calculate T, then we take the moment and divide it by that 28 feet. This is in foot-pounds, so we come out with pounds. So that gives us a tensile force of that 3,857. Okay, then that is simply P over A, but the A is 1 2x4, right? 1 2x4. So that's that, inches squared and pounds, and we come out with PSI. So there's the actual stress on one 2x4, right? It's got 200. It's got 735 psi on it. So now you just have to check that with the NDS and make sure it's going to come out allowable. Okay. So this you look up in the table for spruce pine fir. Number 2, I guess, is what I'm using. So that would be the 450 out of the table. Then you got to put the factors on it. There is no moisture, there's no temperature, and it's not in size. So those all. Wind factor. Okay, we do have that for CD and CF. You've got to look up for tension, right? Oops. So that's in the, you remember where that is? In the supplement, right? You've got to look up that table that tells you, and we've usually been using it for bending, but if you go, I think we used it for compression. Somewhere in there's tension. It'll tell you to use it, what the value is for tension, and that should be 1.5 in this case for 2x4. And I think on the online problems, I think they're all 2x4s. I think I did all with, so that's probably the same for everybody. Okay, so we apply those forces, apply the adjustment factors, and we come out with a whopping 1,800, which is certainly more than what we had up here as the actual 735. So that's okay. So it looks like our spruce pine fir is certainly adequate to carry that load. So that checks that. It's just a matter of checking it in this case. Obviously, if it failed, I mean, online, hopefully it won't fail. But if it failed in reality and you were doing this, you've got a few options. Change the grade, change the wood, change the dimensions of the building. Okay, I don't think you can do that, very likely, but probably control it with the wood and the grade, right? Okay. Well, now what? Now we're going to look at the shear wall. So we've got there's the force coming on it from the drag strut, or the, what do they call that, collector strut. This would be, if I divide that by 28 feet, I think I get that 360. So that's, or no, do I? Maybe I should check that. What is that 360? Yeah. No, that's not right. That's divided by, that's actually, it's funny the way I wrote it there. That's on each of these, PLF. So that should be, where that's coming from is, let's see if this is right, divided by the total width of the shear wall. So 6 and 6 and 8 would be 20, right? 12 and 8 is 20. So what do I get? That should be the 360. 72 divided by 20 equals 360. Okay, so that's where the 360 is coming from. Okay, that's then the load on each of these shear walls. That's that load. The load divided across the entire length, from the diaphragm side, that's the, yeah, we calculated that earlier. From the diaphragm side, that's the 257 PLF, right? Okay, so you see there's a little bit of a difference there, right? The diaphragm has got a load on it of 257, but since there's less area here, these are each going to have to carry a heavier PLF because there's nothing being carried there. Okay, now this is the one that's out of the Spid Whiz, right? Golly, holy smokes. Must be the way I hold it, you think? Or maybe it's how you spell Spidwiz. Not how you'd think. WS. Okay. Right. Okay. So for unblocked, it's 2-to-1. For blocked, it's 3.5 to 1. So I did both here. This for unblocked, I can the minimum width is 8 feet, and for blocked, it would be 4.5 feet. So looking at this, okay, 8 feet, I can do that with the unblocked. If I really was going to have 6 feet here, I guess I'd have to block it. That would, because it's greater than 8 feet. I mean, it's, am I saying this backwards? This is a minimum, and this is less than the minimum. Yeah, I said that right. It's less than the minimum, so you'd have to go with this one. Okay. Again, on the online problem, I think I'm just looking at that center one. But okay. In any case, that you do have to meet that criteria. And that used to be in the IBC, this exact same table. I need to get an updated copy of the IBC. Somehow I was trying to find it in an online version, couldn't find it, but oh well. At any rate, you do have to meet those ratios. Okay, so we've got that, and we've got the shear on the wall. Now we have to look at the because there's a difference between here and here. The force in the strut between them is going to change as it goes across the wall. Okay, did I do that right? Okay, all right. I thought I did that next, but first select the panel for the shear wall. All right, let's do that. This is the table for the shear walls, again out of that the 305, this one, what's it called? X305, I think is where this is. Okay, so I've got, and this is the one you've got to decide. Okay, gypsum, no, I don't think I want the gypsum, so let's not worry about gypsum. Structural grade, no, I don't think I want to use the structural grade, so let's not worry about that. Sheathing, oh yeah, there are a lot of things I don't want. I don't want sheathing, so this is the one I'm using, APA rated. I'm just looking at this part of it, all right, and I've got to find one that carries 360 PLF. So I start with the furthest nail spacing and go down the list. So, and here they're all on 2-inch, I guess they're not. Yeah, this would be on the studs, right? So, no, what am I going after? 360. No, none of those. No, almost that one. So that looks like, my friend, 8 penny, 15-30 seconds. So is that what I got? 15-30 seconds, 8 penny, and 4-inch nail spacing. So that picks that one out of the chart. And like I said, normally that's the way you do it. You start, those ones on the left are the least demanding, right? And as you go to the right, they get stronger, but they also generally get more expensive. So as you put more nails in them, or as they get, I mean, and they're, again, you could pick other ones. I mean, if you wanted to go, maybe something like this would be an advantage, right? It probably doesn't matter whether you're using a smaller nail and it's thinner. Oh, but the nail spacing is higher. So you'd have the added expense of more nails, more nail spacing, but I don't know. It's either one's an option. In terms of that online problem, it certainly takes it wants you to take the first one you come to. Okay, as far as making that decision. All right, now the fun part here, the top chord, checking that. This is the part that's kind of interesting because the force, like I said, varies across it. So this is the diagram we had, right? These guys are in PLF. So you can look at the difference. If I looked at, there's a force here and there's a force here too, right? So I wrote the force here, 2160. This is 6 feet. That force would be 257 times 6, right? 15. So here I've got 1542. So if I I've got 1542 in one direction and 2160 in the other direction, they add, right? Those are the two forces, but they're on the same member, right? So I'm adding two forces that are like this. So when I add them, this one's bigger, so this was the one that wins, and that's the difference then. And we'll take this direction. That direction is negative, right? Whoops, that's negative, and this direction is positive, just to keep track of them. Okay, so that one wins, and that would be the sum of the force. So this is the net force on that collector strut. So over that length, it's got 617 pounds in that direction. Okay, then over here, there's nothing. So this one times, I think this was 4 feet, is apparently 1028. Okay, so there's the 1028 up there. Then on here, I add them again. And this has got, whatever force there. Actually, what I did is I took 360 minus 257, and that's where this number came from, negative 103. So you could just multiply that 103 times the 8 feet, and you'll get the net stress. Because you can do it by force or by PLF, either way. I mean, it's both force, but in the end, you want to get the force though. So here, the net force on the collector strut is going to be in the negative 823. Here again, I've got a 4-foot window. So in this section, I've got the 1028. And then on this end, it's like the same as the start. It's a 6-foot length, so I get the negative 617. So you can see as you're going across that strut, in some places it's in, over the windows, it's in compression, I guess, and over the shear walls, the shear walls are pulling back. It's in tension then, where they're pulling on it. Okay, so you try to chart that going across the wall. So it starts at 0 at the edge of the building. There isn't any force on it, right? So as you move in, now you're picking up the tensile force, and it drops down by the time you get to that point, right? That's that point. It'll be the total for that width was 617, but it'll be a linear transfer. A linear increase until you get to that 617. Then you've got to go from there up to the next point, this one, right? And across that point, it has a constant 1028. I mean, the total force is 1028. So you'll take the 617, or 1028 minus 617, and it'll give you a positive 411. So that by the time you get over here, there would be a compressive force. Now you got across the window, there's no more tension resistance, so it adds up to a compressive force at this point of 411. And then now this kicks back in and is resisting it, and brings it back down to a negative 412 by the end of that, right? That would be at that point. And then again, you've got a window, and it brings it back up to 617, and then the last shear wall brings it back to 0. It should come back to 0 at the end of the, at the end of the wall. Okay, so now you look at these, and again, tension is going to control, and you pick the largest tensile force. And that'll be what you design the whole wall for. And you have to realize, of course, the whole wind could reverse, so this pattern could be the mirror image, right, in this case. But you would design the whole strut certainly for the highest tensile force. So that would be that 617. Oh, okay, so here we go. So here's the 617 pounds over 1 2x4, right? And that'll give me the actual stress in tension on that collector strut. Then this was the same as what we did above. I think it had spruce pine fir number 2 for the wind CD of 1.1 or 1.6, whatever it is for the wind, and the CF factor in tension, right? So we put those two on it. That was the 1080. So wow, okay, yeah, there's not a problem with that. That's going to certainly be okay. So that checks the collector strut. Before we checked this, was it the side strut we checked? Almost forget. Okay, and we've already done the panels, so we've got the panels specified for both the diaphragm and the shear wall. We've got the side, the collector strut. Oh, I know, we checked it, we did the collector strut twice. We analyzed the collector strut for the deflection, the moment due to the diaphragm, and this was the collector strut force due to the resistance of the shear wall. So what we did is we did this collector strut first, if the wind's going this way, right? And then we did this collector strut just now. So this has got the shear, and this has got the bending. So we did both collector struts, and they both panned out to, I think on the online problem, it just asks you pass or fail, I think. Or maybe it just asks you the actual stress, I forget. But they'd obviously have to be the same, right? Because you could have the wind blow from, I guess you'd have to check. We're just doing the wind in one direction, but you could look at the wind in the other direction too. I think we're doing the more severe direction, right? Would be the longer wind load and the shorter shear wall would be the critical case, actually. Okay, now, finally, wall base anchors. Oh yeah, I think we're going to make it here. Wall base anchors. So we got two. We got these end tie downs that we got to worry about, these guys, and we've got the shear in these guys here. So let's see. We've got we're doing that middle wall. It was 8 feet wide. It's 16 feet high, wasn't it? Or no? How high was this thing? How high was it? Oh my goodness!
Is it 16?
Is it 16? Is it? I think it's 6. I think it was 16. Suddenly I draw a blank. Yeah, 16 feet high. Okay, 16 feet high. So we got that. We had, this was given I mean, we calculated it earlier on the shear wall. That 2280 pounds is just on that. We should be able to find where that came from. That should be this. That's that force on that middle shear wall. Okay. All right, and then so that's the 228. I'm sorry, can't write. 2880 pounds. Okay, so then we can get the moment here based on that force as a cantilever, right? And that would be, that comes out to this. And then I want to calculate, that'll be the same moment, right? That has to be resisted, the same, it's the exact same moment down here, is resisted by these two, that couple. So we take the tension times the width 8. So the tensile force then is that same moment in foot-pounds, and the height, the width of 8 feet. So I come out with the tensile, that gives me this tensile force, right? That's that tensile force. So now I have to design a tie down to resist that, okay? 5,760 pounds, or about 6 kips. I mean, and you'd go then to the, I mean, I don't think this is actually in the problem to pick one, but this is where you'd have to go to the literature, Simpson Strong Ties literature, look at their tie downs and find one that does it. I think I do that in a slide or two, but that would be the number you'd be after, that strength. Okay, the base shear of these guys, you just need a shear force. So we've got the studs at 24 inches on center, and there are 8 of them, right? So what do we got? That would be 4 foot. I got 1, 2, 3, 4 spaces. So that's where that's coming from, spaces. And I mean, there are 4 of the bolts, right? That's the number of bolts that's being held down there. These bolts. One more than I showed there. I got one more. Right? 1, 2, 3. This is the other end of it. Would be like, no, one more. Oh, I didn't show this. So I should show 1, 2, 3, 4, 5. 1, 2, 3, 4. One more. 5. Okay. So there's one more anchor there. So 1, 2, 3, 4 anchors, right? Okay, you got it. All right, and then I divide the total load, right, that's on this. That's the 288 pounds. I divide it by that many, and each one then carries 720 pounds per bolt. Okay, so that's just the shear force on the bolt, and that, again, you look up in a table. If you are able to develop the the strength, the pull-out, I mean, should just be the shear force on the bolt. So, you know, the bolt is whatever the steel grade is on that, 35 or something. I don't think they're 36. Whatever they are, it'll maybe give a table that gives the strength of them. Okay, so yeah, all right. Here's the Simpson Strong Tie. We were looking for that. Yeah, this is what I was talking about. They have a ton of these nails. I think you're supposed to stagger nail it. But they probably give you more holes than you need and then tell you how many you have to use. Okay, some of them are screwed and some of them are bolted. Interesting. And we've got a strength. Where's the strength? Oh, here it is. Well, we're on the low side. Look at this. They're much higher ones. So that, even that one would do it. 5980. Okay. And it would require a 7/8 inch anchor bolt, I guess this is the part that's screwed, all right? That's going to be screwed, and this is going to be bolted 7/8 inch, which I guess is cast into the slab, whatever their requirements. But you'd have to look at their literature to see exactly what the installation requirements they specify, because it's all proprietary on their product there. Okay, and then the anchor bolts, these would be cast into the slab. What did we want? We wanted there. That's, oh, I see. Yeah, we wanted 720 pounds, I think is what we want, right? And I'm using a 305 bolt, which apparently is a 36, or 36 KSI at any rate, but only has a shear strength of 10 KSI if you include the threads. Okay, so I guess we do that. And for a 3/8 inch bolt, that's the area. So shear capacity, the F times A, right, is equal to P. So that would be the strength, 742, and we only need that, so we got it. So that would be that bolt, 3/8 inch bolt. So you pick that, and that should be, I don't know, I don't see the strength. They give the specifications down here. I don't see, at least in this table, they don't give the shear strength. I suppose if you looked around online, maybe you'd find one that actually gave you the shear strength of their bolts, but that table doesn't. Not too hard to calculate. Okay, so wow, whew, we made it. That's that problem that's up there. Have a look at it. You got you got your weekend all cut out for you. But do download this. It'll make it a lot easier to step through it, because it marks which parts are being asked in the questions. And then you should be able to step through it. Right? Okay, I think you guys all got your STAD stuff in. That was good job. How's it going with the graphic statics?
I have some questions about it.
About graphic statics? Okay, yeah, no problem. You can ask me
Okay, I ask you
afterwards. Okay. Otherwise, you can. It is very easy to do the analysis with that Dr. Frame. That's why I was kind of suggesting that. In fact, that was posted, my Dr. Frame solution of the one I had as a, that I did in class. You can take that, load that, just open that in Dr. Frame, and all you have to do is move the points, and and it's on a grid. They jump to the dimensions pretty easily, and then if you click on a member, you'll see on the side it tells you the size. If you want to change the size, you just click on it, I think, and it should give you a list for the sizes. Anyway, you can play around with that a little, right? All right, have fun.